All right, today we're pulling back the curtain on something that powers pretty much our entire global, always-on world. Data replication. It's this hidden engine, this bit of magic that makes an app feel instantaneous, whether you're in Tokyo or Toronto. So, let's dive in. So, just think about your favorite app for a second. You post a photo, and boom, your friend on the complete other side of the planet sees it almost instantly. How on earth is that even possible? It feels like some kind of magic, right? Like there's this one giant, super fast database that serves the whole world. But you know, the reality is actually way more interesting. And it all boils down to one powerful idea. And that big idea? It's called replication. On the surface, it's actually pretty simple. Instead of having just one database, you just have a bunch of copies of the same data. We call them replicas, and they're spread all over the globe. Now, all the complexity, all the real magic, is in how you keep all of those copies perfectly in sync whenever something changes. But why go through all this trouble? Well, there are three really big reasons. First, you get to reduce latency. I mean, you're literally putting the data closer to your users so things are just faster. Second, it ramps up your availability. If one copy goes down, no problem, the others are there to pick up the slack and the service stays online. And third, you get to massively increase your read throughput, which just means way more people can access the data at the same time than any single machine could ever handle. Okay, so there are a few different ways you can actually manage all these copies. Let's start with probably the most common and, honestly, the most straightforward approach out there, what we call single-leader replication. You know, the best way to picture this is to think of a shared document, like a Google Doc or something. There's one person, and we'll call them the leader, who has edit access. They're the only one who can make changes. Everybody else, they're followers. They can see the document, they can read it, but they can't actually edit it directly. It creates this super clear, totally unambiguous flow of information. So here's how that actually works in practice. Step 1. A user wants to change some data, we call that a write, and that request goes to the one and only leader. Step 2. The leader writes that data down and then sends that change out to all of its followers. And then step 3. Anybody who just wants to view the data, that's a read, they can ask either the leader or any of the followers. It sounds simple enough, right? But this process forces you to make a really critical decision. And that decision is this. Does the leader wait for a follower to say, "Yep, got it," before telling the user it's done? If it does wait, that's called synchronous replication. It's super safe because you know for a fact the data's in at least 2 places. But it's also slow. The alternative is asynchronous replication. Here, the leader just sends the update out into the void and immediately moves on. It's way faster, but it introduces a pretty serious risk. I mean, what if the leader crashes before that update ever reaches the followers? And that right there brings us to the Achilles heel of this whole single-leader model. What does happen when your one and only editor, that single point of failure, the leader, just disappears? Well, the system has to perform something called a failover. And this is basically the emergency procedure, where one of the followers gets promoted to be the new leader. This lets the application keep on working and accepting changes. But, and this is a big but, this whole process is loaded with some pretty significant risks. See, if you're using that fast asynchronous replication, any changes the old leader was about to send, they're just gone. Poof, lost data. And what's even worse, what if the old leader suddenly comes back online? It might not even realize it got demoted. This leads to a nightmare scenario that we call split brain, where you have 2 different machines both thinking they are the leader, both accepting changes and basically just destroying your data with conflicts.
And even when nothing is failing, that asynchronous speed can create this really bizarre user experience called replication lag. Just imagine this. You post a comment on a website. That write, of course, goes to the leader. A second later, you hit refresh. But this time, your read request goes to a follower that just hasn't gotten your update yet. So from your point of view, your comment, it just vanished into thin air.
Okay, so obviously, engineers have come up with solutions for these kinds of problems. To fix that whole disappearing comment issue, for instance, there's a specific guarantee they can implement called read your writes consistency. It's basically a promise from the system that says, hey, you will always see the updates that you just made. So, to get around some of these limits of having a single leader, especially when you're dealing with a truly global scale, engineers came up with the next logical step, multi-leader replication. Let's see how that works. So with this setup, you might have a leader in each data center. So one in Europe, one in North America, you get the idea. This is perfect for huge global operations. It's also great for apps that have to work offline.
like your calendar app on your phone. And it's actually the secret sauce behind things like Google Docs, where everyone can edit at once. But all this extra power comes with a really big, new challenge.
And here's the absolute crux of the problem. What happens if someone in Europe and someone in North America edit the exact same piece of data at the exact same time? Both of their changes are accepted by their local leaders. So now you have a right conflict. The system somehow has to figure out which change wins. And trust me, getting that right is incredibly difficult.
So, faced with all these complicated failovers and messy conflict resolution problems, some designers took a really radical turn. They just got rid of the leader altogether. And this approach is called, you guessed it, leaderless replication.
This was pioneered by systems like Amazon's Dynamo, and the idea is that a client can send its write request to several replicas at the same time. Any replica can accept a write. And this points to the huge core benefit. If you have no leader, you have no failover process. If a machine is down, the system just works around it. Simple as that.
But wait, how does this apparent chaos stay consistent at all? Well, it's through this really clever concept called a quorum. The system sets up two magic numbers, W, which is the number of replicas that have to confirm a write for it to count, and R, which is the number of replicas you have to ask when you want to read something.
And these numbers are all governed by one simple formula. W plus R has to be greater than N, where N is the total number of replicas. So for example, let's say you have 3 replicas in total. You could set both W and R to 2. A write is only successful if 2 out of 3 machines confirm it. Then, when you do a read, you have to ask 2 out of 3 machines. Since 2 plus 2 is 4, which is greater than 3, your read is guaranteed to overlap with at least one of the machines from the successful write. It's an amazing way to guarantee you get up-to-date data purely through math.
Okay, so we've looked at 3 really different ways to do this: single leader, multi-leader, and leaderless. And the reason they all exist is because there's no single best answer. It always comes down to a fundamental trade-off that you have to make.
So let's just break it down one more time. Single leader, it's the simplest, and it completely avoids write conflicts, which makes it a fantastic choice for most general-purpose apps. Multi-leader is super complex, and you're going to have to deal with conflicts, but it's really the only way to go for multi-data center or offline-first applications. And then there's leaderless, which is kind of in the middle on complexity and risk, but it is the absolute champion when you need high availability. Really, the choice you're making boils down to this: consistency versus availability. On one hand, do you need a system where every single person is guaranteed to see the exact same up-to-the-millisecond data at the exact same time? That's what we call strong consistency. Or on the other hand, do you need a system that is just always, no matter what, online and ready to go, even if it means some of the data might be a tiny bit out of date? That is high availability.
And as you can see here, these two things are often pulling in opposite directions. The more you push for that 100% uptime, for that incredible availability, the more you usually have to relax your guarantees about having perfect, ironclad consistency. And that right there is the fundamental trade-off in almost all modern system design.
So I'll leave you with this to think about. For your bank account, you absolutely want perfect consistency, right? But for your social media feed, maybe availability is what really matters more there. So the next time you open up an app on your phone, just ask yourself, which trade-off did the engineers who built this choose?